Hi, welcome to Redox Reactions Part 8. My name is Dr. English, and today we're going to be talking about another type of electrochemical cell called an electrolytic cell. Specifically, what is an electrolytic cell, looking at a spontaneous redox reaction again, looking at what would happen if we reversed that spontaneous redox reaction, the components of an electrolytic cell, the electrolysis of molten sodium chloride, electroplating, and then finally some similarities and differences between these types of cells. So what is an electrolytic cell? An electrolytic cell is a type of electrochemical cell where an electric current from an outside power source forces a non-spontaneous redox reaction to occur. Now, you might say to yourself, that sounds like a lot of chemistry that I really am never going to use in my life. Well, that's not the case, because if you own a cell phone, your cell phone has a battery in it. And every time you use your cell phone or some type of electronic device, you run down the battery. And when it gets close to so-called having the battery die, you need to get your charger and plug it into the wall. And when you take your cell phone and you put the charger in and you plug it into the wall, basically what you're doing is running your battery backwards. In other words, taking this redox reaction, a spontaneous redox reaction, which is your battery, and running it backwards. So a non-spontaneous redox reaction. So don't think to yourself, oh, I never need to learn about electrolytic cells. You use one all the time just by recharging your battery. This process is also known as electrolysis. And electrolysis literally means electricity coming from electro and lysis, which means to cut. So this whole process is what's happening when your battery is charged. In other words, an outside source of electricity makes the battery run backwards. It's also used to decompose chemical compounds into their original elements. So for example, the decomposition of water back to elemental hydrogen gas and oxygen gas. So let's look at the following spontaneous redox reaction. Solid sodium plus chlorine gas gives me sodium chloride. Nice and balanced. If I was to assign oxidation numbers to everything here, I'd say that sodium would be 0, that diatomic chlorine would be 0, that sodium as part of a compound would be +1, and chlorine would be -1. This reaction is going to occur spontaneously without any outside intervention to form sodium chloride. So literally, if I take a chunk of sodium and throw it into a vat of chlorine gas, after a while, those two substances are going to react together to spontaneously make sodium chloride. When I look at this chemical reaction up here and I think about what's being oxidized and what's being reduced, sodium is going to lose electrons and be oxidized, and I can see that because Na is going from 0 to +1, more positive. The chlorine is going to gain electrons and be reduced, and here's their half reactions right down here. So sodium starts out as 0, it goes to +1. In this case, it's going to lose a total of 2 electrons. The diatomic chlorine is going to gain 2 electrons and form 2 chloride ions. And this, based on everything that we've learned in redox so far, makes a lot of sense. But now, what would happen if this reaction was reversed? In other words, let's take sodium chloride as a liquid, in other words, we're going to melt it, and form solid sodium and go back to chlorine gas. Sodium chloride is melted at a high temperature, really high temperatures, and separated into its original elements of raw sodium metal and chlorine gas. An electrolytic cell forces the reaction to take place by using an outside power source. The sodium ions in the molten sodium chloride will be reduced. Now I know this is going to look bizarre. I understand that. It's okay. We're running it backwards. So your sodium ion, because if I go back up here and I assign oxidation numbers, I can see that Na is going to be +1, Cl is going to be -1, sodium by itself is going to be 0, and the chlorine gas is going to be 0. So all of a sudden now, the sodium, which is +1, is going to become more negative. In other words, it's being reduced. So Na plus 1, it's going to gain 2 electrons because there's 2 sodium ions here, and we're going to form solid sodium metal. At the same time, the chloride ions, Cl minus 1, are going to go to an oxidation number of 0. The chlorine is going to become more positive. So the chloride ions in the molten sodium chloride will be oxidized. And again, we're going from -1 to 0 here. We can see the loss of electrons. I know you're looking at this and you're saying, now wait, I know that metals undergo oxidation and nonmetals undergo reduction. This is typically true unless you're forcing the reaction to go backwards. In a spontaneous reaction, it will happen that way. Metals oxidized, nonmetals reduced. But if you're forcing that reaction using some type of outside power source to go backwards, then everything else is reversed also. And we just sort of have to deal with that. Components of an electrolytic cell. An electrolytic cell consists of the following components: some type of container, in this case we'll just call it a beaker, an electrolyte solution, which we'll describe down here, 2 electrodes, an outside power source such as a battery. The definition of an electrolyte. An electrolyte is defined as an ionic substance that when dissolved in water produces ions which can conduct an electrical current. So it's any type of ionic compound, NaCl, KCl, KBr, anything that's going to break down into ions and therefore is able to carry a current through it. Now this is the electrolysis of molten sodium chloride. Now if I'm talking about sodium chloride being melted here, I'm not talking about something dissolved in water. I'm talking about NaCl with a little L down here. So it's just pure sodium chloride, no water added, because that would be NaCl aqueous. This is, I've melted sodium chloride, which I know sounds sort of bizarre, but it can happen. When we look at this electrolytic cell, the cathode is going to be negative. So when I look at this, here's my cathode, the cathode is going to have a negative charge associated with it. The cathode is negative in the electrolytic cell because electrons are being forced into it by the external voltage source, in other words, the battery. So my battery is right here, and the battery is forcing the electrons, and we can see it happening here through these arrows, the electrons to come through this wire into the cathode, and then this becomes negatively charged. So in an electrolytic cell, the cathode is going to have a negative charge. When this happens, the sodium ions, which we know are positively charged, will be attracted to the cathode, which is negatively charged. That makes sense. So when these sodium ions, and we can see them right here, come over to the cathode, they're going to pick up electrons and be reduced. They're going to be reduced into a solid, and we can see it in this half reaction right here. Here's my sodium ions. They're going to gain electrons and be reduced into solid sodium metal. So we'll give it a 0. On the flip side, we have the anode, and the anode is located over here. In an electrolytic cell, the anode is labeled with a positive charge. So we're going to put a positive over here. The anode is positive in the electrolytic cell because electrons are being withdrawn from it by an external voltage source or battery. So this, again, this battery is pulling electrons out of the anode and forcing them over into the cathode, which we know is negatively charged. So this anode will be positive because all the electrons are being pulled out, and electrons are negative. So because the electrons have been removed, this is going to have a positive charge associated with it. When this happens, the chlorine ions, which are negatively charged, here's one right here, will be attracted to the anode, which is positively charged. This will oxidize the chlorine ions into diatomic chlorine gas. So here comes my chloride ion. It's negatively charged. It's going to come over to the anode. It's going to lose its electrons, so the electrons are going to go into the anode, be pulled out, and pushed over into the cathode. And because they're each losing an electron, they now don't have a full octet anymore. Here's chlorine. Okay, 1, 2, 3, 4, 5, 6, 7. And then here's the 8th electron. And we're going to put brackets around the whole thing. and we're going to say, hi, I'm -1. When this loses this 1 electron, which is right here, when this is lost, all of a sudden we're going to go over and we're just going to have Cl 1, 2, 3, 4, 5, 6, 7. It now is lacking that 8th electron. It's no longer an ion, it's an atom, and it can basically form a covalent bond with another chlorine atom and become diatomic chlorine, which we see right here. And all of these green dots are basically representing this chlorine gas bubbling out of solution and out of the beaker. Now let's talk about electroplating, which is just another way of using an electrolytic cell. So electrolytic cells are also used to electroplate metals onto surfaces. The anode is composed of a metal, such as silver or copper, something along those lines, that can be used to plate an object, such as a fork in this particular situation. So this anode is going to undergo oxidation, and over time you can actually see this silver anode deteriorating and getting smaller, so there'll be less mass as this whole reaction occurs. The cathode is the actual object to be plated, in this case a fork. And then we have our two half reactions down here, which we'll talk about in a little bit more detail. So in this situation, like I just said, the cathode is the fork, which will be negatively charged, because we know my battery up here is forcing electrons from the anode into the cathode, and then my cathode is going to have all these little negative charges all over it. Negative, negative, negative. The anode is the silver metal electrode, which is positively charged. Oxidation still takes place at the anode. So my silver electrode, here's my silver electrode, is still going to undergo oxidation and form silver ions and release 1 electron. So solid silver will be oxidized, and then the Ag+1 ions will be released into the aqueous solution. As we can see this arrow right here showing that this silver ion is coming off of this electrode. Now, 1 electron is pulled out of the anode and forced over to the cathode. So we see this right here, this little arrow showing the direction that the electron travels from the anode into the cathode. The positive silver ion, right here, will then migrate or move over to the negatively charged cathode, in this case the fork. So the product of the oxidation reaction is now basically moving over, because it's positively charged, to this negatively charged fork. Reduction still takes place at the cathode. So this silver ion is going to come over to the fork, which has all these electrons all over it, pick up one of those electrons, and plate itself on the fork, forming solid silver. So the silver ions are reduced by the electrons on the fork to form a solid covering, which we call plating. A comparison of voltaic and electrolytic cells. Here's the similarities between these two types of electrochemical cells. Both use redox reactions. The anode, no matter if you're talking about voltaic or electrolytic, will always be the site of oxidation. The cathode will always be the site of reduction. So those stay constant. So you can use anox, red cat with no worries. And electrons will still flow through the wire from the anode to the cathode. So you can still follow your alphabet. A, B, C, anode to cathode. There are a couple of differences though. Voltaic cells are spontaneous. They're going to react without any outside intervention. For an electrolytic cell to work, you need to have an outside power source, like a battery. In the voltaic cell, the anode is negative and the cathode is positive. The anode is negative in a voltaic cell because that's where the electrons are originating from. The cathode is positive because that's where they're being consumed. In an electrolytic cell, the anode is positive and the cathode is negative. The anode is positive because the battery is ripping those electrons out of the anode, making the anode positive, and shoving them over into the cathode, making it negative. So you have to be careful about the distinction between positive and negative, whether you're talking about a voltaic cell or an electrolytic cell. So what did we learn in this brief tutorial? We talked about what is an electrolytic cell. We looked at a spontaneous redox reaction, and then we looked at what would happen if we reversed it. We looked at the components of an electrolytic cell, the electrolysis of molten sodium chloride, electroplating, and finally wrapped it up with similarities and differences between these two different types of cells. Need more help? Feel free to contact me. Have a great day.